Hello everyone, so in this video let us talk about a hard level problem from LEETCODE. The problem name is put marbles in bags. So let us start. So as you can see, you are given K bags. Okay, remember that. Let's also try to highlight something. Okay, we have K bags. Okay, and you are given 0 index integer array weights, where weight of I is the weight of the ith marble. So you are given K bags and also some marbles, as you can see. Now divide the marbles into K bags. You have to divide these marbles into K bags according to the following rules. Okay, no bag is empty, so you have to put all these marbles in these bags. That is first fine. The ith marble and jth marble are in a bag. If two marbles in a bag, then all the marbles between these indexes should also be in the bag. So which means that you have to take a particular sub array, a part of the complete array. All the marbles have to put inside one bag. I'll tell you with some example on also, don't worry. The last is, if a bag consists of all the marbles from I to j inclusively, then the cost is weight of I plus weight of j. So if I have marbles from range I to j inside a bag, the cost of that bag is the addition of weight of I and weight of j. Okay, that is the overall cost. Now the score is the sum of all the cost of all these K bags. So all these K bags that you have, in which you have like inserted all these marbles, you have the score is actually the sum of all these bag costs. Okay, now you have to find out the difference between the maximum and the minimum score among all the marble distributions. Among all the possible marble distributions, you have to find out the one which has the maximum cost and the minimum cost and find out the difference between them. Okay, let's take some example to understand it more clearly. So what you can see here is that we have this as the weights of the marbles, and you have two bags. Okay, let's say we have two bags like this. Now you have to find out small sub arrays. So you can say that you have to take out sub arrays. Let's say I'll make two sub arrays. Whatever k is equal to that, I have to take out sub arrays. That much amount of sub arrays from this particular, you can say, weights array, and you will take out all these marbles and insert it inside one bag, the another in one bag. So this is one of the possible distribution. Okay. Now, eventually, the cost of the one bag is the boundary, the elements on the boundary. So I've inserted one marble. So the cost of this, because I've inserted this sub array here, is 1 plus 5. I hope you understand. And in this, the boundaries is 1 and 1 only. So in this distribution, in which I have taken 3 marbles, put inside one bag, and one marble put inside another bag, is the total cost is 1 plus 5 plus 1 plus 1. Okay, that is 5, 6, 7, 8, 8. Okay. The another overall possible combination can be, as you can see, if I just move this out, I'll put this one and this. Okay, let's actually make it much more bigger so that it will become more easy. 1, 3, 5, 1. So overall task comes down to that you have to form this number of different sub arrays and find out the one which has the maximum minimum score. So let's talk about one of the possible cases. This, I've taken two sub arrays out of this complete array, and they should be continuous, because if I take I and j, all the arrays in between, all the marbles in between go into the same bag. That's the constraint. Other can be like this. Last can be like this. I hope you understand. That's the overall thing. Now the cost of this combination is 1 plus 1 by 1 plus 1, because you can say the I and j for this subarray is same. I is also 0th index and j is also 0th index. Okay. And the cost of this is the marble on these extremities. The marble value on the extremities is 1 only. Okay. For this extremity, the marble value on the two extremes, that is the two extreme of the subarray, is 3 and 1. For this, one marble is of 1 and another marble is 3. For this subarray, one marble is 5, one marble is 1. For this subarray, the one extreme is 1, another extreme is 5. This extreme is 1, plus another extreme is 1. Total is 3, 4, 5, 6, 5, 8, 9, 10, 5, 6, 7, 8. So these are the three possible distributions of marble in these two bags that we have in the first example. And you have to pick up the one that is the maximum possible distribution, that is this, the minimum, that is this, find a difference between them, that is 10 minus 6, that is equal to 4, and that's the answer. Okay, that is the overall thing that you have to do. Now, how can you possibly do this? That is the whole thing. How can you find out different possible divisions among this and find out the answer? What you can see here is that whenever you have a problem, you have to, as you can see, you have to split this overall array into different segments. And how many segments you have to split into? If k is equal to, let's say, 2, I have to split it in, like I have to put slits like this. You can just assume that there is a large array like this. Okay, let's remove this out first. Okay, this is, and you have to put, let's say, k equal to 3. If you have to put it in 3 bags, I have to put 2 slits like this. So let's say I can make a distribution like this, that all the marbles, all these marbles should go in 3 bags. Okay, the other can be, I can put a slit like this. So this is one distribution, one. So there are different distribution in which I have to put a slit like this. Okay. Now, how much positions are there? Like how many slits I can put? Like how many slits I can put? If I can somehow put a slit like this, the overall score lies on the slit position only. Why? Because if you just understand or like observe it more clearly, what you can see here is that if I somehow just take an example, I put a slit like this and the array is like this: 1, 2, 3, 4, 5, 6, 7. Okay, let's say that this is the overall array weights array that you have, and you have put these slits. What is the cost of this slit? Can you just easily understand? What you can see is that wherever is the slit I have put, I have to take elements, the very starting element, whatever element is till that slit, then after this slit till the next slit, then after this slit until the very end. So what you can see, observe here is that whatever element is on the adjacent side of the slit is taken into consideration. All the elements in between are just waste of us. So you just have to only focus on the slit positions. And wherever I put a slit, the consecutive two elements of the slit are taken in consideration of the cost. And I have to take k minus 1 slits, that I have to take, let's say, k equal to n, or let's like whatever number of slits that you have k. So I have to take k minus 1 slits in this particular array. So if I have to somehow find out the one in which I have to find out the minimum distributions, I have to take out k minus 1 minimum slits. The one positions in which if I put a slit, the two consecutive elements are minimum as possible. Okay. So the overall idea lies is that you have to somehow find out all the two consecutive position elements. So I will find out the sum of all two consecutive positions and sort them out and choose the one k minus 1 that are the smallest and the largest one. Okay, because all these elements will be taken into the consideration. The first one and the last one are also considered, because if I take this as a slit, then these two will be in the, you can say, in the final answer. These, if I put a slit here, these two will be again in the final answer. But in these two arrays, sub arrays, this is taken and the last one is taken. And in this sub array, this one is taken, the last one is first one is taken. So first one and last one you have to like explicitly add, and the other two consecutive ones are just added. Okay, I hope you understand the overall idea. What we are trying to explain here is that you just have to form and find out all the two consecutive elements, take every two consecutive elements and find out the sum of them and put it inside some array. Okay, because, and among all of them, these are the slit possible positions I can put. So every two consecutive elements is the position at which I can put a slit. And if I put a slit there, both of these elements will be there inside the score, final score. Okay, and for minimizing the score, you will put the elements or take the elements that are giving us the minimum score by choosing that slit. Or if you want to maximize it, you will choose the consecutive elements that are the k minus 1 consecutive elements that are the maximum score. Okay, that's it. So that's the overall logic for this particular problem. Let's move on to the code part now. So what we have done is that we have this boundary weight, the boundary weight vector. You will iterate over all the elements, as you can see, and find out the sum of I and I minus 1, the two consecutive elements, and find out the sum of all of them. So this is like the possible slit positions I can put and sort them out. So that I have now all the sorted positions, split positions I can put. Now I will find out the maximum minimum, the maximum minimum k minus 1 positions. I can put a slit. So I will take the first k minus 1 because it is sorted. So the first k minus 1 are the smallest positions, and the last k minus 1 are the maximum positions at which if I put a slit, it will give you the maximum score. Okay. Now you can also add in maximum minimum the first element and the last element, because that is also added inside the score. But in the end, if you subtract them out, both of them has the same values and it will be cancelled out. So nothing matter much here, but eventually like this, just move this out. That is not required. But in the end, you can just print out the maximum minus minimum. That is the difference between them, and that's the answer. Okay, that's a complete logical code part for this particular problem. Nothing much complicated. It's just a greedy solution. Eventually, you can think of it as a DP also, but it is not because the concept is pretty large. Okay, whenever you think of a DP solution, see like the constraint should not be too much large. Okay, then only think in a DP situation. Okay, else it might be solved in a DP, not DP but greedy as well. Okay, so that's the overall logic in the code part for this particular problem. If you still have any doubts, you can mention in the comment box for this particular video. I will see you in the next video, coding, and bye.